Welcome back. Today we're going to talk about 3.5 equation solving and modeling, and what should go along with this should be something that says with exponents or exponential and logarithmic functions. Because the things we're going to look at are going to involve exponents and logarithms. Let's look at a couple of properties first that are going to help us solve some of these problems. Let's say we have two equations. One of them is b to the u, and the other one is equal to, or it's equal to b to the v. If this is true, okay, then u equals v. So if the bases are the same to an exponent, then the exponents must be the same. If log base b of u is equal to log base b of v, then u is equal to v. If you're doing the same thing to a number and the same thing to another number and they're equal, then the numbers must be equal. Using those properties is going to help us, but it's not going to be the full picture. Let's look at a couple of examples. Here I've got an equation where 20 times 1/2 to the x over 3 is equal to 5. I'm solving for x. What am I going to do first? Well, I'm going to start by undoing this multiplication. So I'll divide by 20. So I have 1/2 is equal to, or 1/2 to the x over 3 is equal to 1/4. Well, so what can I do? Well, I'm looking for opportunities to use one of these properties, and if I've got this one which has similar base, here I've got a half, and I can write this as a base of a half. So I can say 1/2 to the x over 3 is equal to 1/2 squared, because 1/2 times 1/2 is 1/4. I'm rewriting them with the same base. And so what I can do then is I could say these are the same, therefore the exponents must be the same. And so if I multiply by 3, then x equals 6. Okay, so if the bases are the same, then the exponents must be equal if they're equal. All right? So let's look at another example. We've got solve e to the x minus e to the negative x divided by 2 equals 5. Let me do a little bit of a rewrite here so you can see it a little bit more clearly. This is the way that's written in your book, but I want to make sure we can see exactly what's going on here. So to solve this, we're solving for x, and so I'm going to first multiply both sides by 2. And so I'm going to have e to the x minus e to the negative x equals 10. To kind of see what's going on here, let me rewrite this part here, e to the negative x. Well, if I've got something to a negative power, it's really 1 over that. And so my next step to solving this equation is going to seem a little out of place until you see what I'm trying to do. I'd love to be able to, because really I need a common denominator, right? But I'd love to be able to eliminate one of these two e to the x parts. And so what I'm going to do is I'm going to multiply both sides by e to the x. So check out what happens. When I multiply e to the x times e to the x, I get e to the 2x, or ex squared. Okay, so e to the 2x. When I multiply this by 1 over e to the x, I really get minus 1 because these end up canceling. See that? And then I get 10e to the x. Well, what do I do with this now? What I can really do is now I can employ a little bit of a kind of a calculus method, and it's going to be based on the fact that this is sort of a quadratic, and I'm going to rewrite it to show you. If I subtract 10 e to the x over here and 10 e to the x over here, check out what I've got. Okay, so I've really got e to the 2x minus 10 e to the x minus 1 equals 0. Well, this is kind of quadratic. And what we're going to do is something called a u substitution, but in this case we're going to substitute a w in. And I'm going to say that w equals e to the x. Why would I want to do this? Well, I don't necessarily know how to solve this one But if I make w equal to e to the x, watch what happens. This would really be w squared, because e to the x squared would be w squared minus 10w minus 1 equals 0. Check that out. Now I actually do have a quadratic. And what I can do with a quadratic is I can solve it like normal, factoring, quadratic formula, graphing, something like that, and then set my answer equal to e to the x. Here's how it works. I'm actually going to put in quadratic formula, so negative 10w, so b negative b plus or minus the square root of b squared minus 4 times a times c over 2a, which is 2. And what I get is 10 plus or minus the square root of 4 times the square root of 26 over 2, which is equal to 10 over 2 is 5. And then this would be root 4 would be 2, so 2 over 2 is 1, so 5 plus or minus root 26. Here's what I know. I know that on this problem, start up at the top of the column here, w equals 5 plus or minus root 26. So therefore, e to the x, because I'm subbing back in now because w is e to the x, e to the x is 5 plus or minus root 26. Well, if I look at the graph here, so I seem to have two solutions. But when I look at the graph here, check this out. I've got e to the x here. What do you notice about the values of e to the x? Check it out. They're all positive. Okay, so I can't have 5 minus root 26. And so really, I just have e to the x equals 5 plus root 26. Because I can't have the minus, because e to the x is not negative, so I can't do 5 minus. And so I've got e to the x is 5 plus square root 26. I'm just going to solve this one like I would any equation that has an e to the x. I'm going to take the natural log of both sides. And so the natural log of e to the x would be equal to x. This one is the natural log of 5 plus root 26. And when I put that into my calculator, I get x is just about equal to 2.31. Okay? And so what did I do? Here I did a u substitution, a double u substitution. I made it into a quadratic, solved it, and then set my factor that my term that I subbed out equal to that answer, and then solved it as I would a regular logarithmic function. And so as we move on to the next example, we need to be aware of solutions that are not necessarily going to be included in the solution set to a given problem. So we may mathematically get that solution, but we need to watch out to make sure they're actually included in the solution that's shown by the graph or is in the range of the function. So as we look at this, I'm looking at log of x squared is equal to 2, and I need to remember this is log base 10. And so if I bring this around the horn, I've got 10 squared is equal to x squared. And so 100 equals x squared. So if I take square root of both sides, I could have x is equal to plus or minus 10. When I look at this, that's one way to do it. Another way to do it would be to say, if I would solve by bringing my exponent down, I could have 2 log x squared is equal to 2, divide by 2, divide by 2. So the log, this wouldn't be squared, the log of x is equal to 1. And so if I bring my 10 up here, I've got 10 to the first equals x, so x is equal to 10. So what do I do with this information? As I told you, we've got to make sure that we have our solutions available, but we want to make sure we eliminate solutions that don't work, but we also need to make sure that we have all the solutions. So for example, if I did this middle process, or this second process here, and I just got 10, is negative 10 a solution? Let's look at our graph. For our graph, here's our graph. I'm going to go ahead and zoom back out. Check it out. The red is our log of x squared, and I want to know where it's equal to 2. That was my original problem, you remember? So log of x squared is equal to 2. So check it out. What are my solutions? If I zoom out one, check it out. I've got a solution at 10, 2, but I've also got a solution at negative 10, 2. So how do I make sure that I don't eliminate solutions? Well, I've got to verify with my graph to make sure that I didn't miss anything, and also I need to make sure that when I solve, I include my plus or minus if that is appropriate. Okay, so I got to make sure I have my complete solution on that. Let's look at one more. The natural log of 3x minus 2 plus the natural log of x minus 1 is equal to 2 natural log x. How do I solve this one? Well, let's look. I've got a natural log and I'm adding them, so I can use the properties of logarithms to say this is actually equal to the natural log of 3x minus 2 times x minus 1. That's equal to 2 natural log x. If I do a little bit more simplification, I could say the natural log of 3x minus 2 times x minus 1 is equal to the natural log of x squared. Well, what does this do for me? Remember those one-to-one properties we discussed? If I've got the natural log of two different things equal to one another, really I can just cut out the natural logs and I can say 3x minus 2 times x minus 1 equals x squared. Well, check it out. This is actually just a quadratic, right? So if I was so bold as to say 3x times x would be 3x squared. And then 3x times minus 1 would be minus 3x minus 2x plus 2 equals x squared. I'm going to subtract x squared because I'm trying to get it equal to 0. 2x squared minus 5x plus 2 equals 0. I've got options. I could factor. I could work on quadratic formula, and I'm going to choose that option. So I'm taking negative b, so 5 plus or minus the square root of b squared, so negative 5 squared, minus 4 times 2 over 2a. A is 2, so this is over 4. Do a little bit of simplification here. 5 plus or minus, and I've got the square root of 25 minus, let's see, 816 over 4 is equal to 5 plus or minus, this is square root of 9 over 4, is going to be either 8 over 4 or, let's see, 2 over 4, which is 1/2, so 2 or 1/2. What is correct? Again, let's check out this graph and see what we have as far as a solution set. So, is equal to 2 or equal to 1/2. Let's see. And I have the first one, but I need the second one. 2 natural log x. Let's see what we've got here. Where are they equal to one another? So here's my solution here, and that's it. So this is the only place where they intersect. So these two graphs only cross at this one point, so my solution has to be just that 2. So check this out. 1/2 is eliminated right here. It is eliminated there. Only 2 is a solution because they only intersect one time. So that's all there is to this, guys. Okay, so as we solve these logarithmic equations, just make sure we're using those properties, those one-to-one properties, or the ways that we simplify by condensing or expanding exponents, and then we can try to find those x's by using a couple of different methods, including quadratic formula or some other things. All right, thanks for watching, guys, and we'll see you next time.